My name is Wolfgang Kalthoff. I work for the company Keysight, and I'm working in the business development department, and I'm especially taking care with my team for the charging technology and grid edge test solutions. So happy to be here. My topic for the presentation today is market trends and solutions to test EV charging technology, basically also under the umbrella of the event, which is future of EV charging. I have prepared a little agenda for you, so basically to answer the question, why is the EV charging interface testing important and necessary? I hope that after my presentation you can give the answer by yourself. I would guide you through the evolution of the EV charging use cases from the start of the e-mobility to where we are now, and also guide you to the evolution of the physical charging interfaces, so what happens to the connector from the beginning to now today, and then also share a little insight about the CCS protocol evolution, and also would like to talk about then, in a summary, about the technology trends in EV charging that we currently see, and also would like to give you a little example about the MCS standardization roadmap. I saw already in the previous presentation that a lot of standards were mentioned there, so I probably keep it short for you. And then also have prepared a little high-level comparison about CCS and MCS. Where are the differences? Are there differences at all? And also another topic that comes very often in the past weeks is where are the differences actually between CCS and NACS, and what is NACS actually? I will conclude my presentation then with an overview of our portfolio that we have here, also the solution that Elaad is using and also DEKRA is using. And would like then to hand over to the real-life demo, to the hands-on demo, where you then also can ask questions or see the product in action. Okay. When we look at the charging use cases 2015 to 2017, what we see here is basically that we have unidirectional charging AC and unidirectional charging DC. For AC, it was still PWM-based during that day, so specified in IEC 61851-1. And for DC, then it was basically DIN spec that was used. Now, if we look at the charging use cases today and foreseeable future, we see, okay, we have in the AC part also now the bidirectional charging included. We have for the DC also the bidirectional charging included. We see a complete new area of application, which is the truck, the mining, but also aviation, so the heavy-duty application here. And then also we see bus pantograph charging, or also automated contacting devices such as a side coupler and underbody coupler. Last but not least, this will come also in near future, already today available, but on a large scale then in near future, will be then the wireless power transfer. If we look at the connectors that were available back then in 2015 to 2017, then we see that we had for AC in the region US and Japan, AC type 1. For Europe, we had AC type 2. You see on the pictures that there is actually a difference in the physical connector design. However, the pin assignment was basically exactly the same, and also the specification was the same in IEC 61851-1. For GBT, same thing. Also, again, physical different connector for the AC side, but also same technology in use, so PWM-based during that days, and same pin assignment. On the DC side, we had CCS DC Type 1 in the US. Same technology used like CCS DC Type 2 in Europe, however, also physical different plug design here. For GBT and CHAdeMO, we have the difference compared to CCS that GBT and CHAdeMO is using CAN communication method compared to CCS, which is using power line communication. And also if you compare GBT and CHAdeMO, communication protocol completely different, and also physical design of the plug looks similar on the picture, but is also different and not compatible. If we look at the landscape today, then we see that we have basically three new connectors here. On the lower left side, you see the NACS connector. NACS basically stands for North American Charging Standard, and that's basically a new name for the Tesla interface that is around in the US for quite some time. Important to know is here that from 2019, Tesla had a technology change. So before they used CAN, but from 2019, the car was also using PLC technology and also was using CCS protocols. So basically, where is now the change? What is happening in the US market when NACS was announced? Yeah, basically, at the end of the day, it's a new connector. And no change in protocol so far. In the middle, you see the MCS connector, megawatt charging system. We had it in the previous presentation already. That is the standard that should address the new high power and heavy duty application. Goes up to 3,000 amps with a maximum specification and 1,250 volts. In total, that makes them 3.75 megawatts. And I actually brought a sample that was provided by Huber and Suna to you. That is basically the intermediate version. So this one specified then up to 1,500 amps and 1,250 volts. So there will then be a bigger brother that is even way bigger, that then can support up to 3,000 amps. Okay. Now, looking at the protocol side for CCS, we see on the left side, basically it started with the DIN protocol, DIN 7121. If you compare, and now, let's check if that works. Works that? No. Could work. Nevertheless, if you look on the protocol specification line and you see the date, then you see 2014 on the DIN edition 2, but you also see for ISO 15118 2014. So basically simultaneous release, or even the ISO 15118 was a little bit earlier. However, as the ISO 15118 standard was very big in scope, was supporting a lot of features, industry has agreed to strip it down and have a little lower specified, or lower in scope at least, version of the standard, and that is then DIN, and that succeeded to be then the global charging standard for the first electric vehicles that supported DC charging. Important to mention is here that there was no encryption, so pretty open, and currently still available everywhere around. And protocol specification, that's also important, is specified in the document DIN 7121. But the test specification, so how to test that the protocol was implemented correctly, is specified in another document, and that is then DIN 7122. This logic actually applies to all the standards. So if you continue then, next level of standard was ISO 15118, now also reality. Important core feature that was introduced to the market was the so-called plug and charge feature. Plug and charge, for those who do not know, is basically the feature to get rid of the RFID card for authorization. So if you drive an electric vehicle, you probably have this pack of RFID card, depending on which vendor you need, and then you authorize if it works. However, this was necessary with DIN, but with the introduction of ISO 15118, if your car or charging station support plug and charge, then you do not have to need to use your RFID card any longer. You simply can plug your car, your credentials are included in the car, and then everything should run automatically. Also here, important to mention, the protocol is specified in -2 and -3 documents, and the test specification is specified in -4 and 5 documents. On the right side, then, we see the further evolution, and that is probably what we all are here for today, and what we also would like to showcase then during our demo, and that is the ISO 15118-20 protocol, and that has the most important feature to be introduced, and that is the bidirectional charging or smart charging. In addition, there is another level of security added. So from DIN, there was none. For ISO 15118-2-3, there was then TLS 1.2, optional for external identification means, but for plug and charge mandatory. And then for ISO 15118-20, TLS 1.3 is mandatory, and there is then no exception any longer. You see on the standard landscape, and I will not read them out all, that also the complexity with this additional protocol is increasing quite significantly because of the introduction of the new features that come along with -20. Now, looking at the consolidated trends in EV charging that we see since for quite some time is the trend to go always into higher power. Higher power means faster charging, means less waiting time at the charging station. That is basically also still prohibiting a little bit the adoption of electric vehicles. However, this trend continues, so we see that on the passenger vehicle side. We see that throughout all charging standards, so not only CCS, but also in the Asian region, for example, CHAdeMO, but also in the Greater China region with the upcoming GBT 2015 Plus or 2023 standard, but also with the parallel standard CHAoG. Here, high power is addressed. Furthermore, second trend that we currently see is the rollout of the plug-and-charge feature. So I'm not sure if you already all drive an electric vehicle or that you use already this feature. The vehicles have that meanwhile, or some of the vehicles have that, and some of the charging stations have that as well. Also important is that here is a next level of EVSE CCS certification planned by CHARIN. So we hope to get or to make progress that we can go live within this year already. And that incorporates then already the ISO 15118 standard. So far, there is a basic level of charging station certification available. For example, can be performed by DECRA, but that consists of the DIN standard and the IEC standards, and the next level then will include the ISO 15118 standard as well. Third trend that we see then is really the smart charging, the bidirectional charging. Currently, I myself talking about the side from the electric vehicle to the charging station, but there is also a big aspect, and that is where Elaad is especially taking care of what is happening behind the charging station when the energy is fed back to the grid, and that is an international issue to solve, and there's a lot of things to harmonize to make that reality. Okay, just as an example here, the standardization roadmap, it's basically a similar slide that my previous speaker had. What I wanted to show here is that a charging interface consists always on multiple standards, and if something is announced, there is a new charging standard, then basically different groups kick off the standardization of different aspects, and unfortunately they also have different timelines. That brings along a little challenge to define a test system. So usually when there is an announcement, we as test system vendor get the request, can we get a test system for that? And then we need to educate also again that we say, okay, there is certain groups, a lot of things are not yet finally decided, and then we continue to do a stepwise enhancement. So focus on the things that are decided and already final, start testing with that, and then we enhance further the test solution as soon as the decisions are made in standardization group. Okay. In this moment, a big thank you for Hugo and Suna. As I said, they provided the sample that is now going around to the right on very short notice. So once again, thank you for that. And if we now compare CCS to MCS communication, then the question is, okay, why isn't it not the same? Well, I don't know the answer basically, but I know the differences. So if we look at the communication method, then we see here, okay, for CCS, it's single-ended communication via control panel line, so power line communication. And for MCS, it was actually decided to go via differential communication via a twisted pair. And also important, CCS is using PLC, as I said, and for MCS, it was decided to use Ethernet, and the standard is called 10BASE-T1S. That's basically a difference, which makes the standards not easily or directly compatible, and therefore we also basically need to enhance our test system. And actually, this decision was kind of a surprise during the standardization as well, and the group that is affected by the decision said, okay, we look at approximately 6 months delay that was caused by the change of the physical layer. And that is a little bit unfortunate, as of course truck charging that has a high interest at the market currently, and 6 months delay is quite a lot of time. The benefit why this decision was made is actually from single-ended communication to differential communication, that the crosstalk characteristic, if you look at differential communication, is way better. Signal calibration is not required, and for MCS it was decided to also use the ISO 15118-20 communication protocol as standard. Now, looking at the Keysight solution portfolio, starting with the hardware solution, we basically drive a modular-based approach. Looking at the application, starting on the upper left side, we have our EV-EVSE charging communication interface tester, in short ComTester. This is a product that is designed for communication test only, so not necessarily power is incorporated here in the testing, but you can do either an emulation test or you can do a complete conformance test for ISO 15118-4-5 or also close to be released conformance testing for the ISO 15118-20. Underneath, you see additional accessories that should provide a higher degree of automation during the charging testing. For example, we have a swipe robot that then can hold the RFID card and swipe at the right point in time at the charging sequence so that you do not need to stand up every time. So if you ever saw the colleagues testing or charging testing, then yeah, to disclose that as well, our colleagues made a long stick and glued the RFID card so that they do not stand up. However, we meanwhile have now the robots, have received a lot of requests that if we can do something, and so these are fully integrated. Besides the swipe robot, we also have a push robot that can then perform push operations at the touchscreen or at the infotainment system of the car. So we use some kind of mounting system that you can then position the robots exactly where they need to be. In the middle, you see our major portfolio consisting of 3 systems. So on the left side with the stainless steel housing, lower left side is the EMC optimized version of the charging discovery system, is used to be put in an anechoic chamber without bringing in additional disturbances. So that's also a challenge. EMC testing still has to be done at a certain or under charging condition at a certain charging level, and therefore you need to have a super clean charging station that is not bringing in additional disturbances into the anechoic chamber. In addition, that is the red box. We have the Charging Discovery System Portable Series. It supports all charging standards, such as CCS, CHAdeMO, or GBT, and it supports currents up to 400 amps and voltages up to 1,000 volts, and also can support conformance testing for IEC standards, but also ISO 15118, as well as GBT-S CHAdeMO. On the right side, you basically see the bigger brother. It's also here owned already by Elaad. It's called the Charging Discovery System High Power Series. Basically, we have increased the current rating already to 600 amps and also 1,500 volts already. And you can see on the right side, there's an additional module available by what liquid-cooled charging adapters can be used. So in total, maximum charging power. If you multiply 600 amps with 1,500 volts, then we have 900 kilowatts to serve. Basically, we are already working today on an enhancement for the MCS parts that are decided. So we also, you saw the sample from our supplier Huber & Suhner for the liquid-cooled charging adapter. That can be also attached to this system already. Of course, then you are limited in terms of power or current and voltage. However, the next system generation then, of course, will address also this super high currents, such as 3,000 amps. Important to mention is that these test systems are CHAR-in approved. So a test system or a test house can use these systems if it is CHAR-in approved to certify DC EVSEs. So already today available the basic certification, but in near future also available then the so-called advanced certification, or extended certification, sorry. On the lower side of the picture, you basically see also that we provide emulators, and we start at low increments from 5 kilowatts up to 300 kilowatts per cabinet, and then we can also switch them in parallel up to the megawatt level so that we are perfectly prepared, and we are basically also the only vendor at the market that controls the whole test system from out of its own portfolio. So most of the other vendors that you find out there, it's always a mixed solution from different vendors. Certain aspects they need to get back to different vendors. Keysight drives the one vendor approach, and that has a lot of benefits, especially when you look at this dynamic landscape, because we only need to talk to our direct colleagues and can solve interface issues, which is easier compared if you approach another company that has then different priorities, etc., etc. On the right side, you see a new addition to our portfolio here as well. It's so-called CCS Charging Protocol Tracer, and that is a tool to capture PLC data either in the field by using an inductive cable clamp or by installing the system either in your charging station or in your vehicle and drive around and then capture the PLC communication data from your roadshow. On the software side, basically similar situations. So we have dedicated software environments depending on the application. Starting on the lower left side here, this is the conformance test automation framework. We support fully automated conformance testing for DIN, ISO 15118-4-5, and in near future also -20 here. In the middle, you see the Charging Discover software. Here we have the focus on the IEC standards, but also on SHA-Demo and GBT. Of course, you can use each software with the same system of hardware. It's simply depending on your application which one is the right to choose in the right point in time. Below, we have also a new addition to our portfolio, and that is the so-called EV-EVSE Smart Charging Emulation software. That's also quite a handy tool to simply enable a quick charging station and do just minor parameter modifications. And this environment already today, and you will see it in the demo later on, supports already ISO 15118-20 protocol testing for either EV emulation or EVSE emulation, focusing on DC and bidirectional power transfer and other aspects of ISO 15118 to follow shortly. On the upper right side, then you see the CCS Charging Protocol Trace Viewer. That's basically a PCAP file decoder that we serve here. Comes very at an interesting price level and is definitely a usable tool if you have decoded PCAP data and you want to, if you have encrypted and you want to decode them. So, okay, now showing the solution overview, and what is nice, as I explained already, the one vendor approach is that we have the plan to combine our test solution then at the end of the day to an end-to-end test solution. And that especially becomes interesting when we look at the grid side here, because then we can go from the input completely to the output, back in the grid and back and forth. All our equipment is bidirectional. That means also the total cost of ownership are quite reasonable because you circle the energy in the loop. And so you do not have big losses because the systems are also quite efficient. Okay, that's basically my last slide. And with this, I would like to turn this over to Robert and probably Sven.
Thanks. Yeah, you can hear me. Before we start the demo, I will do some short explanation about what we are going to test and what we will show you. First of all, the demo is behind you, but you can all stay seated. It will be displayed on the screen, and we will make sure you can see everything that is happening. Let me introduce myself. I'm Robert Italiaander. I'm an electrical engineer and a technical expert in the ELAAD test lab. I've been working here since 2022. And I'm a project manager. And actually, my first project I did was the installation of the Keysight. So I'm quite happy that we can show it to you today. I'm going to do the demo together with Sven. He's there. Maybe you can introduce yourself shortly. Can you put on the handheld, Rien? Yeah.
Can you hear me?
Yes.
Great. So yeah, my name is Sven Gröning, working as an R&D manager by Keysight since 2021 with the acquisition of a company was called Verisco. And I'm actively working also in standardization since 2010, something, when everything started to develop the first test protocol for the DIN standard we have seen today. And today I would like to show you the demonstration back here. I think we have a camera working here together with Robert, how about 15118-20 implementation can be used with our systems. Coming back later. Thanks.
Thank you, Sven. Okay, Thijs already explained why we test, but I quickly repeat it. As you might know, DC fast charging is getting a bigger and bigger role in the charging of EV, therefore also getting a bigger role on the grid impact it makes. We as a grid operator want to be able to measure it and want to be able to know the impact on this on the grid. Therefore we need to measure, and therefore we need equipment. we also want to improve our interoperability testing that we can offer. So when we are finding a problem between an EV and a charging station, with the Keysight we can really pinpoint where it went wrong and help the OEMs to improve their products. And lastly but not least, we want to test the newest technologies like vehicle-to-grid, like plug-in charge. Okay, now I'm going to explain what kind of devices we have. The testing system has 3 main devices. The first one is an AC emulator. We need that emulator to, hey, it doesn't work, unfortunately. To make a clean grid, so at the left side you see a grid, can be distorted. For testing the power quality, we need a clean grid. But we also need to create a controlled disturbed grid, like the transients, the voltage sags and swells, and harmonic injection. Right now we can only do that up to the 50th harmonic, but that's what it is. So that are the AC emulators. We have 4 of 90 kilowatts, so 360 kilowatts in total. We also have a DC emulator. We need that to create a DC source. At one hand, to provide the power to charge a car, or dissipate the power that is given by a charging station. Like also Tim told us in their presentation, the voltage of charging can have an influence on the power quality. And with this system, we can create all kinds of voltages. So it can from 100 volt up to 1000 volts. So we can see what is the power quality of certain chargers at certain voltage levels, and we're not dependent on a battery. The last thing is the charging discovery system. Yeah, that's basically the brains of the system. Like Wolfgang told you, we can connect the DC emulators to it, we can connect the AC emulators to it, cars, charging stations, we can connect it to our back office. Yeah, so it's taking care of the control and the communication part. Yeah, now I'm going to explain the test setup we have right here. The first test branch we have is for EVSE testing. So over here we connect the AC emulators to the grid. The AC emulators are making a clean grid that we can connect to the charger. Then the charger is connected to the charge discovery system, and the charge discovery system is connected to the DC emulators, which are connected to the grid again. So we have, yeah, in the loop, so we don't only use the energy that is dissipated. The second test we have is for EV testing. Instead of putting a charger to this charge discovery system, we put a vehicle to it, and then we can, yeah, test that vehicle on smart charging, vehicle to grid, 15L8-20. And the last one is man-in-the-middle testing. So we can place the CDS between the charger and the EV, so we find some charging problems. And I think now it's demo time.
Yeah.
So the first demo setup is this. We're going to test Keysight against Keysight to show you that it's able to work with 15L8-20. Then we're going to use a real charger. Going to use the MB box, and afterwards we go test the test system on full power. So we use a bigger charger.
Also, the reason is that it's tough to find a vehicle that supports ISO 15118-20 as a specimen. But we can start the demo with this one.
Yeah. So I think you can take over, Sven.
In the upper part here, you can see that we are operating as an EV. As Wolfgang already mentioned, it's not that easy to find a car already today which have that implemented. This is why we try to emulate it today. You can also see kind of measurement for the proximity, for the control pilot here, and also the power part. On the left side here, you see then plotting over time about all the measurement data. And on the right side, you see a list of parameters you can modify. This is based on setups that you can, let's say, emulate different kinds of EV with different voltage level, different amperature, different maximum power. Also, in terms of timing, you can modify your timing behavior for all the kind of messages which are sent and received. And this is what you can see up here in the called progress bar, which is indicating which step you are in during the protocol exchange. So a lot of messages are going back and forth between the electric vehicle and the charging station, doing a ramp up of the charging station to build up a session. Then you have authorization, you have charge parameter discovery, so what are my maximum and boundaries, in what kind of boundaries we can operate. Then you have a cable check for safety reasons. We have seen that already in various kind of presentations up front. And last but not least, we end up in the charging loop, which is already at the very end over here. Yeah, and then you only have a welding detection and session stop. This is just closing down then the charging process. So what I try now to start is a charging process with the, let me unlock it first.
Top is locked. Thank you.
Yeah, so you have maybe seen in the upper part here, let me check the mouse, that the progress was pretty fast, so there's a lot of messages going back and forth. And right now we are already in the charging process, but you can see here over time there was a ramp up of the current and first of the voltage to check the cable, then going down and then ramp up the current for the charging process. Right now we are in the charging mode. We also have an overview on the lower part here about the session data, which we see what is the actual data sent back and forth in the messages. And you can also see here the logging information, how many loops are already done for the communication. And if we now go in the charging environment, which is back here, if we go from charging to discharging, you will also see that we go here in the negative part. So we are now powering energy back to the grid, and you see also that on the blue part here that we have charged with not much, but we drop down then to a discharging of about 10 amps here. This is, let's say, the normal setup that we can showcase that 1511.8-20 is working with DC bidirectional. Okay, so next setup will be that we stop the process. We have also here two options. You can do it in your car, press the stop button, or also at the charger to press the stop button. I will just do it here from the car. And now we would switch over to our next demo setup. So that was just test system against test system, where we use the Ambibox, which are also here today. And we can plug out the test system, plug in the Ambibox system.
Go.
And yeah, we will try the same again. So same parameter set, just another system under test. And you can also see that we go to the specific parts of the process. But now you can also see if something unexpected happened, that it directly stays in red, and you see, okay, something went wrong. Yeah, so you need to restart? Okay. So what we have seen is just that the charging station stopped, and we can then see, okay, it went from the state B here to state EF. And we will start one more time. So there's no signal from the charger coming.
We need to plug it in and out.
Maybe try.
It's always the same with demos. But
But
be patient.
it's live.
It will work.
So there's no duty cycle coming from. Okay. Yeah, then maybe we skip this first for now. Maybe after the session, if we have another break or coffee session.
I think during the drinks, we'll make sure the demo is working and you can check the
yeah, we can then
the
start
demo
over
with the
again.
empty box, which is doing bidirectional charging. Then I think we go to the last
Okay.
last setup. Can you change the parameters? The last setup is the high power testing setup. We connected the ABB charger over there to the CDS. First the EC emulators, and then we connected to the device on the test. And that's also the point where we measure the power quality. So we measure on voltage and current, and we do that on really high bandwidth. We do it with 1 megasample per second. Then we connect the charging station in the CDS, and the CDS is dissipating the power to the DC emulators. Sven is right now doing some other parameters, so we can up to high powers. In the meantime, I will connect it. And maybe we can switch back to the testing screen, so you can see what Sven is doing. He is restarting the test. Runtime, yes. Yes, this one. Cool. And then we need to fill in some parameters that we are making sure we have the right power. This can take a while. Maybe I can tell you some interesting facts about the building. We're here in an old, Axel Nobel building. We used to make glass fibers over here, so I don't have more interesting facts right now. So we wait. Okay. So this can take a minute.
Yeah, so maybe you can also see here that a lot of protocols you can choose, but I think we will start with the old one, with DIN.
Then yes.
Then we also want to start with the power flow. We want to.
Now we're setting up the car we want to emulate. Oh, something.
So we go with 950 volts.
Indeed. So we set the maximum voltage of the car to 950 volts, and then we say the maximum. It's that one. The maximum power is 330 kilowatts. We fill that in. That's the amps. So yeah, the. Okay. We state what the initial battery voltage is and what the battery voltage is that we want to climb to. So we start with 900. We want to go to 920 volts. And we need to, yes, 920. Yes, and we need to disable those buttons. Yes, active power flow is on. So I think we can start the test. We can shoot this one. Charging loop. Yeah, there we go. Sure, maybe we can zoom in on this number. Is that possible? Yeah, I think that is possible. Yeah, as you can see, the active power. Oh, it's a bit. Go back. Yeah, the active power flow right now is 330 kilowatts. That is going from the grid emulators to the charging stations and back to the DC emulators again. I think that was the last demo. Yeah. Maybe some time for questions?
Yeah, sure.
So we, yeah. Shall we stop it? Yeah. It's a bit noisy.
Okay. Thank you for this great demonstration.